I'd like to welcome everyone to our webinar this morning. Thank you very much for joining us. So we're running this webinar for the class project as part of the BDVA webinar series. So thanks very much to BDVA for their support in organizing and promoting this. Our webinar today is titled A Highly Distributed Software Architecture for Real-Time Big Data Analytics over the Complete Compute Continuum. I'm Nicoleta Chiapidou. I'm the dissemination leader of the class project based at the Barcelona Supercomputing Center, BSC. And I will make a very short introduction, introducing the agenda, our speakers, and then we will go ahead with the presentations and the Q&A. So very briefly, just going through the agenda of this morning. So we have with us first Eduardo Quiñones, the class project coordinator. Eduardo will present the class project and give an overview of the class software architecture. Then we have Roberto Caviccioli, researcher at Unimore, who will talk about the edge analytics and use cases of class, and he will talk about the smart city case in detail. Then Eli Kartsakli, senior researcher at BSC. Eli will talk about the distribution and orchestration of real-time analytic workflows over heterogeneous distributed infrastructures. We have then Ruth Palmero, project director at Atos Research and Innovation. Ruth will talk about the deployment and lifecycle management of containerized applications through Rotterdam. And finally, Ereth Haddad, research staff member at IBM Research Haifa, who will speak to us about the class analytics fabric. We will then, after we finish the presentations, we will have a Q&A slot where people can ask questions. You can use the chat to ask your questions, or during the Q&A slot or during the presentations. You can also use the Q&A feature of Zoom if you wish, or you can click on raise hand, this feature at the bottom of your Zoom window, and I can unmute you. So thanks very much for joining today again, and I think we can start with our presentations. So Eduardo, I give the floor to you. You can share your screen.
Thank you very much, Nicoleta, for the presentation. And thank you for the attendees for attend this meeting, this webinar. Okay, so today I'm going to present the class project, and more precisely, I'm going to provide an overview of one of the main innovations that we are developing in the class project, that is the class software architecture. Let me, however, before start providing a very general information about what is the class project about. CLAS stands for Edge and Cloud Computation, a highly distributed software architecture for big data analytics. It is a project that is under the scope of the ICT 16 call that was issued in 2017. It is a 42-month project, meaning that it will finish very, very soon in end of June, and the budget is 4 million, and the participants are BSC, that also acts as a project coordinator, the city of Modena, Acerati, University of Modena, IBM, and Atos. So let me start about why we decided to start the class project. So traditionally, data analytics executes mostly at the cloud. Why is that? Because in the cloud is where all the computing muscle is where large data sets are, and so where most of data analytic occurs. And traditionally, edge computing has been mainly used for data filtering and data transfer due to the very limited computation capabilities. The type of data analytics that traditionally executes at the cloud level is called data at rest, while the one that executes at the edge level is called data in motion analytics. However, there are a number of reasons that makes this paradigm not to scale anymore. So one of those is, for example, that data sources are more and more geographically distributed. And this puts a lot of pressure, especially on the network side and on the cloud level. And here, the smart city application domain is one of the best examples. Another important issue, and this is one of the focus of the CLAS project, is that there are more and more applications that not only requires to provide performance in order to implement the data analytics, but also requires the fulfillment of other non-functional requirements, as it is the case of real time. This is the case, for example, in the automotive domain, in which some data, the result of some data analytics is needed for the functionality of the cars. And so real time can be as important as providing the level of performance needed. And then there is, of course, the classical 3V challenge, that there is this constant increment on the volume and the variety and velocity of a data set. All this makes this paradigm not to scale anymore. And so what we are proposing in the CLAS project is to really coordinate better edge and cloud resources, so data analytics can take full benefit of what we call the full compute continuum, including both edge computing and cloud computing. And this is exactly what is the vision of CLAS. The vision of CLAS is that what we want is to significantly increase the capabilities of the data analytics of the newest smart systems, such that we can integrate both what has been traditionally data in motion and data at rest into a single workflow, so it can take benefit of the full compute continuum. By providing this sense of full continuum, our vision is that we will be able to provide the real-time requirements that some of the system needs, so that we can provide those analytics that are more time sensitive to edge computing, rather than sending this to a cloud. And here it is fundamental to introduce into the compute continuum the most advanced parallel and energy efficient embedded platforms, so we can provide to the edge computing the computing muscle that is needed in order to implement the data analytics, and especially data in motion analytics. And if there is a key word that the CLAS project is pursuing, is productivity. We want to do all this such in a way that the software development productivity is not affected. And it is not affected from three different angles. First, we want to provide programmability, meaning that the programmer, that the developer can describe the data analytics workflow independent of the underlying platform. The second angle we want to address is portability and scalability, meaning if partially or completely the compute continuum resources changes, the data analytics workflow needs to be changed. Does not require to be changed, or changes are minimal. And the last one, we want to provide the level of performance needed to implement these workflows, but not only performance to cope with the newest functionality, but also to guarantee this performance so we can provide real-time requirements. And so how the class project envisions to do this. And here I see, I don't know why, there should here appear some of the logos of the tools that we are using, but they are not appearing. I don't know why. I hope that during the next presentations you will be able to see the type of technologies we are using. So the main contribution, as I was saying, is we want to integrate technologies from different computing domains into a single development framework that we call the class software architecture, so we can efficiently develop these complex data analytics workflows and execute it across the compute continuum. And so what type of technologies this software architecture introduces? So it introduces a powerful API for the development of advanced data analytics methods, including programming models that are used in big data and in high performance computing. We are also including serverless and compute and container as a service cloud technologies that has been enhanced in order to provide quality of service. We are also including advanced orchestration methods to allow the workflow to be scheduled and deployed across the compute continuum in a time predictable manner. And of course, as I was saying before, we want to include into the software architecture the most advanced parallel programming models to exploit the performance capabilities of these embedded parallel and heterogeneous processor architectures, such as CUDA, such as OpenMP, such as OpenCV, etc., etc. And oh, that's a pity because I don't. So let me just stop here 1 second. I don't know why, but my pictures, I don't see my pictures. Let me stop again. It is important that my picture appears.
Sure, Edu, we're waiting, no problem.
Okay, thank you. So
in the meantime, I have shared
this.
some links in the chat for people to check our website and the software architecture.
It was working like 5 minutes ago, and for whatever reason, now it's just stopped working. So let me try again.
Otherwise, I can try and share.
No, I think I have a new version. So let's see this new version. Okay, very good. Okay, that now you can see the picture. Okay. This is, for example, one of the pictures that it is an important one in which appears some of the members of the team that are working in the class project. Okay, I'm going to skip this part. These are the logos I was talking about. I think it is important to mention them. Okay, so and then this class software. So we intend we are implementing, we are applying, we are testing this class software architecture in a very ambitious yet realistic smart city use case that it is deployed in the Modena Automotive smart area in the city of Modena. The Massa is a 1 kilometer square living lab urban area that includes IoT connectivity and the needed compute continuum infrastructure in order to deploy and execute complex data analytics workflows. And we also have 3 connected cars that are equipped with sensor and V2I communication. And so here the idea is to develop, deploy, and execute data analytics workflows across the compute continuum that allows the city and the vehicles to exchange information among them, so the urban mobility is enhanced. And here we are focusing into use cases. Mainly, the first one is related to the computation of the level of pollution that the vehicles at a single vehicle granularity level emits in real time, and also the introduction or the use of the information that the city collects for advanced driving assistance systems. And that is where the real-time requirement is very, very important. And Roberto later will talk about the 2 use cases that we are addressing, that are having the virtual mirror, that is allow the car to see behind the buildings, and also allows and what we call the 2 source of attention. So the city is the second source of attention for vehicles. And let me very briefly try to provide an idea of how the software architecture, the class software architecture, is being used for the implementation of these use cases. This is going to be better explained during the presentation, during the next presentation, but just let me try to wrap up all what I've presented. So let's, for example, consider a case in which you have one pedestrian that is crossing, and there is a car that is equipped with sensors that could be see this car perfectly, but there is a track that is preventing the car to see this pedestrian. However, there are 2 cameras from the city that can see, can detect, and can identify this pedestrian. In order to implement this use case, we would need a number of data analytics methods in order to detect the different objects, track them, try to identify when the same object is seen by 2 different sources, compute the trajectory, determine if there is a potential collision or not, and alert the vehicles about this collision. And so here the question is, okay, how are we using our software architecture, our class software architecture, in order to easily implement, deploy, and execute this workflow? So the first thing we have to do is to use this powerful distributed data analytics API that allow us to describe the workflow and how the different data analytics methods relates among them. Okay. Then there are in the city, there are a number of computing resources at the edge and at the cloud level that can better suit depending on the data analytics. So we can use the different software architecture components for example, exploiting the performance capabilities of the edge level, distribute the compute, orchestrate the distribution of the different analytics across the compute continuum, use serverless function in order to speed up functions at the cloud level, or provide quality of service at the cloud level using a new container as a service methods. And so this is what during the next presentations my colleagues are going to try to explain. Okay, and to conclude my talk, the message I would like you to bring from home about this presentation is that CLAS is aiming to develop a software architecture that will allow the development of this complex workflows, data analytics workflow, efficiently combining data in motion and data at rest with the objective of increasing the development and deployment productivity of those systems while guarantee the real-time properties. And we aim to apply this software architecture into a realistic use case with two advanced urban mobility applications. So thank you very much for listening.
Thanks very much, Edu, for this overview of the CLAS project. And I think we can go ahead with Roberto's presentation. Roberto, whenever you're ready.
Okay, let me just share my screen. Okay. I hope everyone can see.
Yes.
Okay, so thank you very much, Nicoletta, and hi everyone, and thank you for joining us. I will now introduce the MASA infrastructure in which the CLAS project is developing the software architecture that has been described by Eduardo. Then I will describe one of the use cases that we are deploying, which is the most complex one in terms of the real-time constraints that we want to comply within the CLAS project. And finally, I will present the analytics that are deployed on the compute continuum. So let's start from the infrastructure set. The MASA area is here depicted on the left, and it's a metropolitan area behind the Modena train station. There are schools, there are health center, a library, a shopping mall, a startup incubator. So it's a very complex and living area. And all of the area has been infrastructured with optical fiber to have a high throughput and low latency communication. We have also a private 4G antenna for a private 4G network that has been used in the project, and which allows us to have a very low latency computation and communication within the vehicles that are in the area. And we have also a 5G prototypal antenna and a lot of traditional cameras and some smart cameras that we have prototyped, have yet to be installed, but are on the process of being installed. As of now, we are monitoring 16 traditional cameras in the area, but we are installing 12 double optics smart cameras. So the coverage of the area will be actually increased. The more powerful edge nodes that we have and the cloud servers are installed in the new data center that has been recently built in the area. Then, within the area, we are going to drive 3 smart vehicles, which are fully equipped with sensor to perceive the environment and send metadata to our infrastructure. Each vehicle, as you can see here, is equipped with 6 cameras for 120 for a 360 degree and 260 degree camera for a frontal view, 3 radars, and 1 360 LiDAR, which allows a complete view and the correct positioning of the objects that the car is sensing around itself. For a good precision about the position of the car, we use a high-end GPS antenna on the vehicle. Also, all of these sensing data are processed by means of an automotive-grade compute platform and communicated to the MASA infrastructure through a 4G modem on the car. In particular, for this version of the vehicle that we have here, we have an NVIDIA Drive IGX Pegasus board, 1 Auster LiDAR with 128 different level of scans, Seconics cameras, and an Xsense GPS with also as an integrated inertial motion unit, or IMU. The radars are the only ones that are already installed on the vehicle, and therefore we read the data of these radars through the CAN bus of the vehicle. And, so let's just now discuss what is the most complex use case that we have to tackle in our project. The target is to have a real-time obstacle detection and collision prediction that will send warning signals to smart vehicles and connected vehicles. Just to clarify, what I've just shown to you is a smart vehicle, which is a vehicle that is able to perceive the environment. On the other hand, a connected vehicle is just a vehicle with a GPS and a small embedded board which is able to connect to the 4G private network. Since the software architecture is scalable, as shown, and as it will be shown from my colleagues in the next presentation, we imagined 5 different scenarios in which the road users might be in need of external help. We call this virtual mirror and 2 sources of attention, as described by Eduardo before. Let's dive into a couple of these. So scenario 2 is an example of our virtual mirror situation, and it has been already described by Eduardo. It means that the class software architecture here is able to create a digital twin of the city and to provide a look around the corner feel to the users that are in the area. In this case, the smart car, therefore a fully sensorized one, is in the process of overtaking this truck or garbage collector. In front of the truck, there is a pedestrian that is going to cross the street. And the sensors of the car are not able to perceive the pedestrian because they are occluded by the truck. But the city cameras have a free view of the scene, and the infrastructure can send an alert to the car. And we will see later how these alerts are sent. On the other hand, scenario 5 that we imagined is what we describe as 2 sources of attention. Why? Because here we have a connected vehicle, not a smart one, which is exiting the parking lot behind the train station and entering the traffic. On the right, here there is a roundabout with a pedestrian which is crossing the street, while on the left there is a vehicle approaching. The glance of the driver might be focusing only on the pedestrian or only on the left coming car. Therefore, the information about a collision that might happen due to the near road user behavior is very useful for the driver. Now, I would like to describe more in detail the analytics that is distributed over the compute continuum. The detection of the object that we are doing is performed by means of a deep neural network on each camera, from which we obtain the corresponding bounding boxes. Then we convert the lower middle point of the bounding boxes to the correct GPS position of the area by means of an homography that is computed differently for each camera. And finally, this GPS position is converted to meters to permit the computation of the speed and the orientation of the vehicle from a tracker that we deployed. We had to benchmark different versions of our object detection network because we have dual needs. We would like the highest precision in detecting the different road users while maintaining the latency requirement of the project. Here we train different versions of the state-of-the-art YOLO, you only look once, object detection network with different data sets as well. In particular, we use the well-known COCO dataset and the Berkeley dataset. Depending on the level of the compute continuum in which we deploy this network, we can tune and we can choose the version of the network that is working better for our needs. In particular, if we want to use the full precision, the half precision data type, if we are more interested in the highest precision that is here with the YOLO v4, but we have lower precision. Just to clarify, all of these numbers are taken on a NVIDIA TX2 embedded board, but on our fog more powerful edge nodes that we can call also fog nodes, there are NVIDIA Titan Vs, and therefore these performances are much higher on that kind of equipment. After the detection, we have then to track the object to assess the speed. We filter the object depending on their GPS position using a nearest neighbor technique, and it is implemented by means of a KD tree for speed and performance. Then we feed an extended Kalman filter to filter the noisy data and predict the future state of the road users. Since the Kalman filter is very lightweight in computational request, we can have a tracker updated for each object that we detect in the area. Now, hoping that you can see clearly, even if you are in remote connection, in this video we show the detection and the tracking of the objects. The trajectory of the road user here is drawn in the lower part of the bounding box, and when it changes color with a different color, it means that it is a different tracked object. Even if, as you can see here, the green object is still maintaining, the pedestrian changes. Why that? Because sometimes the detection is still not seeing for all the frames the same object, and therefore it misses the detection and changes the ID of the detected object. Here we can have a bird view of the same area that has been seen in the previous video, but with only the trajectory of the vehicles and the road users depicted. Here the area is limited, as you can see, but the same knowledge that we have here of all the trajectories computed is obtained from all the cameras and the connected vehicles that we have in the area. Now, how we predict the trajectory of the object. We have an algorithm in the class software architecture that is able to compute multiple predictions per object in different future time points. Why is that? Because we have, for bicycles and cars, it's quite easy to understand that they are going through a straight line, while for pedestrian is much more difficult. Input samples also are not equally apart in time, because depending on the frame rate of the videos, their compression, and the time of arrival to the algorithm, it's difficult to have a constant delta in time to be updated in our algorithm. And also, we need to predict trajectories for multiple objects at the same time. So the core trajectory prediction needs to be applied to each object that we have in the MASA, and only when new location data is available for each of the objects. Here is an example of, let's say, of the X and Y output of the trajectory prediction, so the GPS of the X and Y, using a range of 200 milliseconds. In blue, there is the detected path, and in orange, the predicted path. As you can see, the prediction starts only after a while, because we need to instantiate the prediction of the tracking, and then when we have at least some point, we are able to predict where the object is going to be. And then when we have the trajectory prediction for all the objects that we have in our data knowledge base, we are able to predict if there could be a collision between two objects. The collision detection is applied to each pair of street objects that we have, let's say car, pedestrian, bicycle, buses, and so on. And the collision detection then computes the predicted path intersection. It is computed a quadratic regression to get the functions for the two objects that are in scope, to be able to get the possible intersection that we have in the future. And when the two trajectory functions are defined, we cross them, and if exists an intersection point, we get the timestamp of the object, we predict when this should happen, and therefore we can have a decision and say, okay, if within 2 seconds these objects are going to collide, we send a warning to them if they are connected road users, let's say a connected car or a smart car. And we send it as this kind of information. So we have a warning with the possible objects and the position, latitude and longitude, and certain point in time in which the collision might happen. And then, if we are on a smart car, we have a visualizer that allows us to display the warning alert. And this is the warning that we can see here. This car is starting, the other is approaching. Here we have a fence, and here we have the warning that a possible collision is going to happen. So this car is able to stop before the collision actually happens. So thank you very much, everyone, and I will...
Thank you. Thanks, Roberto, very much for your demos and presentation on the class use cases. Very interesting. So we can go ahead with Ellie's presentation now. Ellie from BSc, whenever you're ready.
Hello, everyone, and thank you for joining the webinar. Let me try to share. Wait. You cannot see the presentation mode, right?
No.
Again. Here.
Yes,
I think now it's okay.
Yeah.
Okay, so welcome everyone. I will talk about the distribution and orchestration of the real-time analytic workflows over the heterogeneous infrastructure we have in class. So first of all, I would like to talk about the challenges that we face in the distribution of the workflows. So, okay, the concept of distribution has been around for a while. It is about executing workflows in a distributed way over a network of systems that share the resources as a common pool. But now with the evolution of telecommunications, networking, cloud computing, and also with the requirements passed by real-time services, we are arriving to the new paradigm of edge computing. So in edge computing, we have a layer of smart devices, IoT devices like sensors, actuators, connected cars, etc., that generate a lot of information that can be processed to provide real-time services. However, even though some of these devices have processing power, such as the smart cars or the smartphones, this processing power is relatively limited. So this is where edge computing comes into play, and we have this edge layer here that can take on some of the processing, some part of the processing of the workflow. And since it is located close to where the data is generated, the real-time response, the response times are low enough to provide real-time services. However, the processing power of the edge layer is still somewhat limited, so we need to offload any tasks that do not have latency constraints to the cloud. So in class, we see all these available resources as the compute continuum that spans from the edge to the cloud. And the challenge here is to orchestrate the distribution of our workflow analytics over this whole compute continuum in such a way as to fully exploit the resources and provide real service guarantees. So the challenges are, first, we have to deal with massive data generation from geographically distributed sources. For example, in class, we have a network of cameras and we have the smart vehicles. Then the interconnection of all the smart devices and the available infrastructure takes place through heterogeneous networking. So different technologies might be used with different constraints, different characteristics, etc. So this affects the response time of the analytics. And finally, we have heterogeneous computing infrastructures that vary in terms of processing power, which can be from very powerful cloud servers to Raspberry Pis, for example. They vary in architecture. We can have CPUs, GPUs, etc. And they vary in execution environments, from containers to different virtual machines or operating systems. So the question is, how can we deploy complex analytic workflows over this highly heterogeneous infrastructure? And how do we tackle with the distribution of the different tasks? So even though most applications now tend to follow the microservice paradigm, it's still very challenging to determine where to place each of the different components. So the answer that we provide in class is by using COMPSS, which is an open source framework for the computation distribution that is being developed by BSc. So it features a programming model and a runtime system. And if you go to the web page, you can see a longer description and a list of the potential advantages of using COMPSS, but I will only mention the three most relevant ones for the class use case. So first of all, COMPSS has a programming model that enables us to develop workflows that support parallel and distributed execution while following the sequential programming philosophy. So it is relatively easy to take a code written in Java, Python, or C and transform it to a COMPSS distributed workflow. Then COMPSS is agnostic of the underlying infrastructure. And by that, we mean that even though we have to declare the available resources that form our compute continuum, or provide a mechanism to discover these resources on the fly, once this is done, then COMPSS will handle the distribution of the different tasks, and the programmer does not need to know where each task has to be deployed. And finally, COMPSS is seamlessly integrated with a distributed data store called data CLAI that handles the distribution of data and the availability of data wherever it is needed by the analytics. So I will provide a specific example on how to develop an object detection application using COMPSS. So this example is inspired, of course, from the class use case presented by Roberto in the previous presentation. And it is a subset of this use case that we actually use in class. So let's assume that we have a camera covering this intersection in the mass area. And we want to perform object detection, tracking, the duplication in case we had more sources like smart cars or more cameras, and then create a data model where we put all the information obtained by each frame into a specific data structure that we call a snapshot. Now, in the complete use case of class, this data model, these created snapshots are then federated to the cloud to be used by further analytic processes such as the trajectory prediction and the collision detection. But in this example, I will only focus on this part of the workflow. So how do we go on to develop such an application? So first, we have the sequential code. We, for example, for these 4 logical modules, we define 4 different methods. First, we get the detected objects from the camera by obtaining the output of the deep neural network that Roberto presented before. Then we pass these detected objects to the tracker that tracks the objects and determines if the objects were present in previous frames and assigns the same ID, or assigns a new ID to newly detected objects and extracts their GPS position. Then if we have multiple trackers covering the same area, we deduplicate them to have a single appearance of each object. And finally, we create the snapshot with a data CLAI model. So the main function will be like a for loop to get all the detected objects and track them in case we have multiple data sources. In our example, we only have one. We deduplicate and we create the snapshot. Now, how do we convert this to a distributed workflow? Well, with COMPSS, we only need to add this decorator task and declare the different dependencies. For instance, if we go back to the function declaration, we add this descriptor, and for the tracker, we note as a dependency the input of objects detected by the deep neural network and the objects tracked in the previous frame. And then if we have multiple trackers tracking the information from frames corresponding to the same time slot, then we need all this collection of the detected and tracked objects to be entered to the duplicator. Furthermore, COMPSS enables us also to determine any hardware constraints. For example, if we want for some reason to limit the execution of this data model creation to a specific node, we can declare it like that, like a hardware constraint. So then at the runtime, COMPSS will create the task dependency graph, ordering all these dependencies that were declared previously. So for instance, a graph corresponding to the example that we said before would be something like this. This line here shows the dependency between the object detection of 2 consecutive frames. And this line here shows the dependency of from the output of one tracker to exactly the tracker of the next frame. Now, this might look simple, but in the real application, where we would process several frames at the same time, the tracker would be much more complicated. For example, if we process 1 second of video frames with a frame rate of 30 frames per second, we would have 30 tasks, for example, for the object detection, 30 tasks for the tracking, etc. So the task would be far more complex. And if we had more cameras, where, for example, in class, we will have streams of up to 16 cameras, you can imagine that the task dependency graph would be much more complicated. So the advantage of COMPSS is that it generates all these tasks and then handles their distribution in a way transparent to the programmer. So we don't need to preoccupy ourselves with where to distribute all these tasks and where to put, how to transfer all the dependencies, all the necessary data information. This is handled in a way that is transparent to the programmer. So how does this distribution works? So let's consider this example that resembles to the MASA computing infrastructure. So we have an edge node that is called aggregator. And we also consider here 2 fog nodes. In the actual MASA infrastructure, we have 3, but it is the same. And let's assume that the camera is connected to fog node 1 and data CLAI is deployed to the aggregator node. So let's say that COMPSS has a master and worker architecture. So we deploy the master at the aggregator node and we execute the main function there. And in runtime, the main function will generate all the tasks and then handle their distribution. So the first step would be to deploy the workers to all the available resources and then distribute the different tasks based on some scheduling policy. So as I said before, for example, in here, let's assume that the object detection and tracking is assigned to fog node 1 because it's closer to the camera where the data is generated. And the generation of the snapshot is hard limited to be executed at the aggregator node because we marked it as a constraint. And the deduplicator runs at a different node. Now COMPSS will handle the data transfer of all the dependencies, all the list of tracked objects and detected objects wherever they are needed. Now, what about the scheduling? What is the orchestration for the distribution of all these tasks? Well, COMPSS comes with some baseline orchestrators that use the FIFO scheduling policy. But in class, we have implemented an advanced orchestrator that considers the real-time properties of the system. So the first step for us is to proceed to have an offline profiling in order to measure the execution time of the tasks and the data transfer times. So before actually running the final use case, we need to have a profile for all the available compute resources to obtain the different execution times of the tasks and the latencies introduced by the communication network. So once we have this profiling, we can apply different scheduling policies that all share in common that they aim to minimize the response time. So we have tested with an optimal solution, mixed integer linear programming model that is, of course, is optimal, but is computationally intensive. And we have also tried with some heuristics that are suboptimal, but have a very good performance and limit the complexity to a more tractable level. So the outcome of these scheduling policies is that they minimize the response time and are able to distribute the workflows in the way that allow us to have some real-time guarantees. Now, one key detail is that this allocation of the tasks happens in a static way for each scheduling iteration. So we define scheduling iterations as a number, for example, of frames that are processed in parallel in the example before, let's say that we have 1 second of processing or 10 seconds of processing, it doesn't matter. We generate the task dependency graph for all these tasks, and then we allocate them applying our scheduling policy. So since we have the profiling information, this allows us to estimate an upper bound for the execution, also applying some margins. So this allows us to have some real-time guarantees. Also, despite the fact that the allocation is static for each scheduling iteration, overall the allocation happens in a dynamic way, because for each iteration, we can proceed to the reallocation of resources that is triggered in case we detect changes in the compute continuum. For example, we detect that a node is down or a new resource is added, and whenever the real-time properties are not met. So if we notice that the delays that introduced exceed our desired level, the COMPSS orchestrator will try to reallocate the resources to obtain a different response. So having an example with that, let's say, for example, that fog node 2 goes down. So COMPSS will automatically detect that the tasks there are not executed or they take a lot of time, exceeding the estimated latency. So they will take these 2 tasks and reallocate them to the other available resources. Also, another feature that my colleague Ruth will explain later is that we can also have dynamic offloading of the tasks to the cloud. So for the object detection use case specifically, we only use the edge resources, because at least up to the tracking and creation of the snapshot, because we want the computation to happen at the edge. But still, COMPSS is connected to the Rotterdam Container as a Service, and if needed, it can request the deployment of COMPSS worker at a dynamic way to the cloud. So Rotterdam will get the requirements from COMPSS, create a pod cluster and a Kubernetes cluster, and deploy and scale as many workers as needed. So summarizing, we have seen how the class software architecture and the COMPSS workflow orchestrator are employed first to design and distribute the complex analytic workflows over the compute continuum in a way that is transparent and agnostic to the programmer and agnostic to the infrastructure, and how using our orchestrator we can provide real-time guarantees and ensure the dynamic reallocation of resources and scaling on the fly to meet the real-time requirements. So that's all for me. Thank you.
Thank you very much, Ellie, for your presentation. Great, thank you. So I think we can go ahead with the next presentation, that of Ruth Palmero from Atos.
Hello, thank you for giving me the floor. Thanks for the attendees. Okay, I think, can you see my screen? Yes.
Yes, perfect.
Okay, I will talk about the deployment and lifecycle management of containerized application with Rotterdam. We will see how Rotterdam helps to implement the class continuum, the class computing continuum, to improve it with quality of service enforcement, and also how we have improved also our several level agreement with prediction to provide time guarantees. So this is the class continuum computing platform that is deployed in Modena data center. We have two clusters that works as private clouds, an OpenShift cluster and a Kubernetes cluster. On the Kubernetes cluster, we have our Rotterdam, is a computer as a service orchestrator. That is also part of this Rotterdam is our CLAI, that is actually the component that will make sure that the quality of service is fulfilled. So from the developer will have to define in a very simple JSON which are the characteristics of the application that is going to be deployed together with the quality of service to meet. And Rotterdam will make sure that this application is being deployed. It will follow all the life cycle of the application. And in case the quality of service is not being met, it will make sure that it can be move to, it can be scaled or move to a different application so that the time guarantee is fulfilled. So Rotterdam is our computer as a service and allow the deployment of and management of a containerized application in Kubernetes. It can control not only applications, but also the COMPSS workflows in the context of class in multiple infrastructure like Kubernetes, OpenShift, micro Kubernetes, kubeless, and so on. Thanks to the SLA Lite, that is a part of Rotterdam, it provides application the scalability and elasticity triggered by the quality of service rules defined by the user. And this is done just by a simple REST API and a JSON format and a JSON file to describe the generalities of the application or the workflow, and also the quality of service needs. This is an example of the Rotterdam API. For example, how you can control to get information from the task, delete tasks, create new tasks, and so on. And this is an example of the JSON file that is transferred to Rotterdam, is feeded to Rotterdam from the REST API with the description of the application, or in the context of class, the COMPSS workflow that needs to be deployed. So it's very simple JSON file. It has the number of replicas. The number of replicas is the concept of number of workers, and as it was explained by Eli in the previous presentation. And it also has the name of the template that defined the quality of service. In the case of COMPSS, is also deadline missed. The concept of deadline is also from the previous presentation. We also have the capability of implement serverless functions. It will be a very similar JSON file. And with this information, our service level agreement component will create an agreement. This is the agreement that we will make sure, or Rotterdam will make sure, that is going to be fulfilled all the time. So from this template, we have in the initial file, we have 4 replicas that are the COMPSS workflow is expected that are needed to perform the workflow in the time that is needed. And from here, we will use this information to create the agreement. In the agreement, we will see that the constraint is that the metric defined by the deadline message has to be less than 1, means it doesn't have to produce any deadline message. And in case this constraint is not fulfilled, then we have the action, that the action will be to scale out, to produce more number of workers than the initial number of workers. And the scale factor will be 1.5. So with this information, the COM masters pass this information in the format of a JSON file to Rotterdam. Rotterdam will call the SLA Lite to produce the agreement, and also COMPSS is going to transfer the metric with the information of the deadline, the state of the deadlines, to our Prometheus. SLA Lite will check the Prometheus for the metric that is supervising, and in case the quality of service is not being met, then it's going to take the action. It means that from 4 initial workers that were deployed, it is going to scale to 6 workers. Okay, so this is how we meet the time guarantee. But we have realized that in some cases, job ahead of this scalability make it difficult to meet make it difficult to make the quality of service. So that the time that it takes to pass from 4 workers to 6 workers, and also the time that it takes to realize that the quality of service is not going to be met, will make it difficult to, in the end, get to the time guarantees that are expected. So we have improved our quality of service of our SLA with what we call the SLA predictor. And the idea is, what if we could predict what is the optimal number of initial workers instead of expecting in real time to scale this number of workers. For this, we have introduced a new model that we call the SLA predictor. And in this case, before creating the agreement, the SLA manager is going to ask the SLA predictor with the information of the initial number of workers and the expected execution time, and base it on previous execution, and well, actually is a training, is a machine learning, is a model that is trained. Based in this model, it is going to reply with the optimal number of workers to fulfill the tasks without having to scale. So as you can see, we have changed the quality of service. Instead of the deadline missing, we have changed it by 2 parameters: the expected exec time and execution time, and the number of initial workers, that is the replicas. With this information, we call the SLA predict for and the number of the seconds of execution time, and we obtain the number of expected optimal number of workers. This is the same example that we saw in the previous slide, so that we saw that it was 6. So how we have designed the SLA predictor? When we have done an exploratory data analysis, and in the end we have used a classification model in which we define the state of the system in 3 states: either low, normal, or high. And depending on the state of the system, how stressed is the system, and the number of workers and execution time, we have this rules definition for linking workers, stress, and execution time. So for a specific number of workers and the actual state of the system, we obtain the frame of execution time, and we see if it is possible or not with the initial number of workers, or what is the number of workers that are optimal. To obtain this stress, we have used this stress level, we have used a number of metrics that define the system. So in this presentation, we have described how we use Rotterdam to deploy and control the lifecycle management of containerized application. It can work in different infrastructure like micro Kubernetes, kubeless, in cloud and edge, with a simple REST API and a simple JSON to describe the application, and also provide the possibility to supervise quality of service admit. And we have also described the SLA predictor that helps to produce informed quality of service rules to optimize the scalability and elasticity of the life cycle management. And this is all.
Thank you.
Thank you for attending.
Thanks, Ruth, very much for your presentation. Very informative. And I think we can now go ahead with the last presentation of today's webinar, that of Ereth Haddad.
Do you see my screen now?
Yes, not on presentation mode though.
Yes, and now in presentation mode.
Yeah, perfect. Okay.
Excellent. Let's go. Hi everyone. I'm Erez from IBM Research Haifa, and I'm going to talk about the class analytics fabric. That is the infrastructure that spans cloud and edge that allows several analytics application to collaborate, several analytics component to collaborate and form together complex applications. So first I will start from the application view. This is a general, high level view of the class analytics application of collision avoidance. And we will see it consists of actually several analytics components that collaborate together. First, I'm going right to left. So first we have some components in the field that collect data. We have sensors, static sensors mounted all over the massa, as Roberto just talked about. And also, you saw in Roberto's presentation, the cars are instrumented with sensors that do some computation, collect data, and convert it to eventually the data that comes from both the cameras and the cars is converted to a stream of anonymized objects that are classified only as as to the data that they pertain to. For example, we have cars, we have pedestrians, bicycles, trucks, etc. And each of these objects is repeatedly detected. So this is one analytics application of generating these streams of objects. And then we have each of these objects is repeatedly detected and thereby has a history of locations of different locations at different timestamps. Based on this history, we then perform a trajectory computation. Also, you saw that mentioned in Roberto's presentation. So this is another analytics application that generates a predicted trajectory in the near future for each object. Then we have another analytics application, which is the collision detection, that takes the predicted trajectories of objects and tries to detect a possible collision based on path crossing or path proximity. And the result of which is a collision warning that you saw also in Roberto's presentation that is then sent to the car. So how can we have multiple analytics components collaborate efficiently in a single environment? So this is the idea of the class analytics fabric, which by design we chose to base it on a serverless infrastructure. We use Apache OpenWhisk. This allows us to bind objects, to bind computation, first of all, to events. What are possible events? Event can be a reception of a network message. It can be a direct invocation coming from another component over the serverless protocol, which is the uniform mediation that allows different components to talk to each other. Some sensor data, user input, or even timed events. The response can be any kind of the analytics backend. So we have MapReduce in LitOps, we have workflows in COMPSS, we have neural networks, we have PCP, which is complex event processing. And all of this is governed by the overall workflows coming from COMPSS, as well as the data backbone of class, which is data CLAI. So before I dive into the discussion of the value of using serverless as a foundation for the class analytics fabric, I would like to first give a short overview of a developer's perspective of how to develop a serverless application from components. So the way you start as a developer is you simply write a code function. So here is a simple code function. This is a hello world function. It takes some parameters and returns some value. What OpenWhisk or what any serverless platform imposes is some structure on how the parameters are received. For example, OpenWhisk insists on using a JSON structure and returning value in JSON, and also some formats of the function name, which is quite secondary. Then the important step is to deploy this code function, this code file or collection of code files as a serverless function, which converts it into an entity that exists in the serverless ecosystem. So we have this command of OpenWhisk, the WSK command, which allows us to take this code and convert it into a function. Once it is converted into a function, now it can now be invoked just like any other function, only by using the serverless protocol. So we invoke we created a function hello, we invoke it this time with no parameters. So according to the code, it uses a default and we get a return value, which is hello world. Okay. But the nice thing about the serverless platform is once the function is created, we can now bind it to an event. How do we do that? We start by creating an event trigger. You can think of an event trigger as kind of a pub/sub channel to which functions are subscribed, so that every time an event is published on the channel, the subscribed functions respond by doing computation on the event using the payload of the event as its parameters. So the next thing, of course, is to bind the function to the event trigger. So we take the function, we created the trigger my trigger, we bind the function hello to the trigger my trigger using a rule, which we call my rule. And that's it basically. Now, I'm not going to go into the technicalities of how an event is triggered. That can be done using CLI, using API. But once every event is triggered, the function will respond by doing the computation on the event payload taken as parameters. And the nice feature we see about this also of the serverless platform is auto-scaling. What is auto-scaling? Basically what it means, it's not important how many events are created, and even concurrently, the serverless platform will make sure that a function instance is created in response to every event and handles that event automatically with no further responsibility of the developer. So now that we know a little more, for those who did not already know what a serverless platform is, I'd like to share with you some lessons we learned of using the serverless foundation as a foundation for class analytics. So first I'll start with the good stuff. What was it good for? So as I said, it's event driven, and since class is mostly about responding to event, that's a very good fit. It also supports direct invocation, which allows collaboration between different components. It supports auto-scaling, which relieves that responsibility from the developer. The functions are deployed in isolation, which makes it good for using shared infrastructure such as a commercial cloud. The overhead imposed by the platform is quite lightweight, which means you get good density on both edge and cloud instances. The platform itself is highly inclusive and comprehensive. That means functions can be written in different programming languages and use different analytics backend, and yet collaborate to form complex applications, which is a very important property of class, spanning cloud and edge and being universal in approach. And the last important advantage is rapid prototyping. When you build a serverless application, you start with supporting just one flow that you want to support, and then you add more functions and event and expand your implementation to a full application. What wasn't so great with using serverless for class? So first of all, when you develop applications using a serverless, you notice that your functions are essentially stateless. What does it mean, stateless? A function is spawned in response to an event, which means it's spawned out of the blue. It doesn't know anything about the current application state. It needs to retrieve that state from somewhere. One way we do that is by pushing some information through parameters, and another is by asking the function to retrieve data from data CLAI, which is the class data backbone. These are also the customary ways of mitigating statelessness in developing serverless applications. Another aspect, since class has a strong focus on real-time, is initialization and finalization overhead. Because when a serverless function is created, so first there needs to be created a container, and then that container is populated with a function code. And then once the function starts running, it may have some initialization overhead, such as, for example, retrieving state from data CLAI. So all of this binds together to an initialization overhead, which might become quite significant. So how do we mitigate that? We leverage an effect that is popular with serverless platform, which is called the warm start. That is, once a function is started, once it is finished doing processing of one event, it is still kept in memory, so that in case another computation is required, you use the already initialized instance. So this is warm start, and we leverage that quite extensively. Another issue we leverage to mitigate finalization overhead, for example, you need to drop a database connection or do some logging or statistics, is that you execute the function asynchronously and continue computation as soon as the result is ready, and not wait for the entire function to complete. A final aspect that we saw is when you use a serverless platform, that means you use the scheduler of the serverless platform and not one that you use. One significant mitigation of that was using the warm start, which also allows us to mitigate overhead caused by scheduling incompatibilities, so to speak. But another more important aspect is the scale control. What do I mean by that? When as I said, the serverless platform features auto scaling, which means that instances are spawned in response to events. But unless you configure the platform properly, you might create too many instances and then cause CPU, memory, or I/O bottleneck. We mitigate that by, of course, doing proper tuning of the platform to match the available resources as we see fit. The second topic I would like to talk about with respect to the analytics fabric is to cover one analytics backend and how we adapted it to class needs. So I will talk about LitOps. LitOps is a Python library for doing massively parallel computation on various backends. We use it in class to do the trajectory prediction and the collision detection, since these applications are massively parallel in nature. They consist of operating on a large data set where each computation is independent from one another. So how do we use that in LitOps? LitOps basically offers two main operations, a map and a reduce. It's a map reduce engine. A map operation takes a function and a data set and applies the function to every element of the data set, yielding a new data set. Reduce is similar to map, with one difference, that the function is applied to elements of the data set with an accumulator, thereby yielding a single result or a data set of a different size. The idea, of course, of using LitOps to these applications is that you can increase parallelism up to some significant limit and thereby significantly reduce the total latency of the computation. So how does LitOps work? The LitOps client code uses the client code that we write. For example, the trajectory prediction application uses LitOps as a library and calls the map operation. Once it calls the map operation, LitOps takes the data set that is given to the map as a parameter and dispatches invocations to serverless functions with each of the map function with each of the elements of the data sets. So assuming that we have, for example, a concurrency limit that we define in OpenWhisk of up to 4 concurrent functions, you get a behavior that is similar to this. The problem is that LitOps originally is not really suited for real-time computation. So by taking an example benchmark of, let's say, one of the Modena videos that you already saw, where we have an intersection and a pedestrian, there were 21 objects there. We realized that the collision detection there took up to 4,000 milliseconds, 4 entire seconds, which makes it completely impractical in the time it takes to notify the driver up front to make sure that the driver has enough time to stop before anything dangerous happens. So we were able to optimize using that benchmark to under 350 milliseconds, which makes LitOps significantly more fit to purpose when it comes to being used in class for trajectory prediction and collision detection, up to almost 12 times faster. How did we do that? First, we optimized the data preparation, the part where we engage with data CLAI to retrieve the state. That was joint work with BSC. Then we optimized the worker launch so that it used far less I/O. We removed some components. LitOps traditionally used to rely on object storage for passing information to workers. We used some direct invocation where possible and switched to a message queue protocol, which is far faster. And then, as I said, we leverage warm start better by using a round of warm-up before starting the actual computation. We move the session connection in memory, which saves us significant amount of initialization time. We did all sorts of additional optimization. One final important optimization I just like to mention is using chunking. Chunking is, as you can see here, when each element is invoked is invoked independently, and you have a maximum concurrency of 4, which is in this example, you get these gaps between the different computation, which amount to a significant type. Why is that? Because each invocation needs to first finish and then restart. So this is responsible for this gap. By chunking multiple invocations together, you eliminate this accumulated gap and can save significantly on the total latency, which, as I said, the overall result was making LITOPS far more suitable for the class goals. The next topic I would like to talk about is the Edge Analytics agent, or more broadly, how do we make class analytics span both cloud and edge? So the difference between an edge node and a cloud node is that cloud nodes are typically tightly coupled. They have highly reliable and fast communication between them. They share a common scheduler, a common control plane, and all that. In contrast, edge nodes are loosely coupled. They have a communication with the cloud that is not always reliable. They are independently managed. They are independently scheduled. Yet we want to give the class developer an approach where that developer can deploy his or her code in one location and make sure it runs in the designated edge nodes just as it would be in the cloud. So how is that done? We use the federation protocol. The federation protocol allows propagating software assets from one OpenWhisk instance, which we designate as the leader instance, to multiple follower OpenWhisk instances, which means we deploy OpenWhisk as one instance, for example, in the class cloud, and as additional instances in edge nodes, including possibly the car, the street nodes, etc. Each of these follower OpenWhisk is actually a programmable agent of the leader OpenWhisk. Then the federation protocol guarantees the propagation at scale of the deployed software assets from the leader instance to the follower instance with eventual consistency. That means within a finite time, the instances are guaranteed to be deployed at all the designated nodes. So now I'm going to show you an example. We took a class detector, which is a component that is developed by Unimore. Roberto presented it earlier. This detector is used for detecting the objects in the edge nodes. It is running in the edge nodes in the smart cameras. And it is deployed as a single instance in the class cloud and then propagated as an update to all the edge nodes. How is that happening? So note that the detector is a long-running stateful Docker service for edge nodes, which means it's not an OpenWhisk component. Yet we were able to propagate it using the same federation protocol. How did we do that? Whenever we have an update for the detector, that update is pushed as an updated Docker image to a Docker registry. Then the federation command, what it does is create a project manifest. The project manifest is an OpenWhisk asset. It's actually a file that lists components that are comprised together a single OpenWhisk project. These components don't have to be OpenWhisk asset. They don't have to be functions or event triggers or anything else. They can be pretty much anything. So we put the tag of the updated registry inside the manifest, and we propagate the manifest to the edge nodes. In the edge nodes, we have an OpenWhisk function that is bound to a timer event. It wakes up periodically. It checks that for the current project manifest. It sees now in the project manifest that there is a new tag. Then this action handles the update of the service. What it does, it first pulls the updated image to the edge node. Then it gracefully shuts down the existing instance, and then it starts the new instance on the same node. So to summarize my presentation, I talked about three main highlights of the class analytics fabric. First of all is the foundation, which is a serverless infrastructure. It's event-driven, polyglot, auto-scaling, very effective in terms of making developers' life simple and thereby making developers productive, but it also suffers from some limitations such as statelessness and initialization, finalization overhead. And I discussed how we mitigated this in class. Then I showed how we took one analytics backend that leverages parallelism to reduce latency, and we adapted it more specifically to class needs for the purpose of trajectory prediction and collision detection. That was the LitOps. And you also saw an earlier principle also demonstrated in Ellie's presentation, the same principle of leveraging parallelism to reduce latency in COMPSS. The last topic was using federation to make class analytics span both cloud and edge. That's it. Thank you very much.
Okay, so yes, just summing up and thanking everyone for joining our webinar today. Many thanks to our speakers and to BDVA for their help and support for this webinar. Stay tuned with the class project by visiting our website, our Twitter and LinkedIn accounts, as we have many activities coming up because the project is coming to an end at the end of June. So thanks very much for joining us today and stay tuned.